Welcome back to Boiler Wild. My name is Eric Johnson. On this podcast, talk about boiler industry topics as well as personal development. Wild is the name of this podcast. Boiler Wild. Wild stands for work hard, invest yourself, lead others, and develop yourself into a person of excellence. Today we're going to be talking about stack temperature of a boiler. And by stack, I mean flue gas temperature and whatever else you want to call it. So there are some other general names, but typically people say boiler stack temperature or flue gas temperature. Your flue gas temperature is an indicator of your boiler efficiency and its health and how it's running. You need to pay attention to your flue gas temperature, whether if you're a service technician just working on a singular boiler and you're just going in between a boiler and sites, you should always pay attention to the flue gas temperature. Or if you're a boiler operator and you have boilers that you watch all the time, you should be honed into the flue gas temperature, and a small change in temperature, you should immediately know something's happening. If you're a building owner, building operator, facilities person, a change in flue gas temperature will show up as a change in your bill of your utility cost. So let's get into it. First, we need to understand that your flue gas is a symptom of what is happening. So I like to break down boilers into simple terms. A lot of people, if you're newer to the industry or newer to a boiler, can overcomplicate it. A boiler is just a vessel to exchange heat. It's essentially a heat exchanger. And whether the boiler is a fire tube boiler or a water tube boiler or whatever else boiler design you want to call it, you'll have water on one side of a surface and you will have combustion gases or fire on another side of that surface. And the whole point is for your combustion gases to be transferred through to the water. Now, we can't have fire underwater that I know of, so you have to put a surface in between them. And typically that surface is going to be some kind of metal. In a Scotch Marine boiler, it's going to be a carbon steel. If you get a condensing hot water boiler, it's going to be some type of stainless steel. There's also copper fin tube boilers, but it's going to be some type of metal that separates the fire, which is essentially just a type of energy, and we are trying to transfer that energy to the water in order to heat the water to either just pump it on a hot water boiler or to turn it into steam on a steam boiler. So the first and probably most common insulator that is going to affect the energy transfer between your combustion process and combustion flue gases to your water is going to be soot. Soot is like unburnt carbon. It's going to be, if you've never seen it, it's black and it's like really fine particles or flakes, and it can stick and build up on the combustion side of the boiler, and it is a great insulator. I don't know why it's a great insulator. I haven't looked into the chemistry of it, but for some reason, unburnt carbon is a excellent insulator. And 1/32 of thickness is equal to about 8% of heat transfer loss, which can add up to be about 3% of increased fuel usage for the same amount of load. And then if you increase it to 1/8 of an inch, think about how small 1/8 of an inch is, you have an estimated heat transfer loss of 47%, which can increase your fuel by 10 to 15%. Why this is important. So if we are insulating our heat transfer surface and all things stay the same, so we have the same amount of energy on the fire side, and we reduce our heat transfer efficiency between the fire side to the water side, that energy has to go somewhere, and it's going to go up your stack. With the amount of energy costs we have nowadays, that is not ideal. So that is the number one indicator is soot. Why does soot build up? Typically, soot builds up on linkage burners. That's probably the most common one because linkage gets out of adjustment. You'll also have soot buildup, especially on heavy oils or solid fuels. That's a big one. There's this thing called soot blowers. They're not common on smaller boilers, but on large industrial boilers, soot blowers are common, and they are essentially a device that can knock off fireside debris that affect heat transfer. But you want to avoid soot. If you come across a boiler and the fireside is sooted, you will notice your stack temperature is 100, 200 plus degrees over normal temperature. And it can get hotter. And it's not one of those things where you can just like let it go. Oh, we're going to just go another month. If something is causing sooting, it's only going to get worse, and the heat transfer is going to reduce less and less, and you can get into a dangerous overheating situation. You can also have too much soot build up. Soot built up in the right amount can become explosive and catch fire. So that is not good. So what to do? You shut the boiler down, clean it out, which is always a fun process if you haven't done it yet. If your employer asks you, hey, do you want to clean a sooted boiler, or you're going to go clean the sooted boiler, you're going to be in for a fun time. Number 2 is scale. Scale is buildup of minerals on the water side of your boiler. Scale, if you're not familiar with it, is essentially like almost is like a potato chip. It is a flaky material, but it can build up hard. And if it builds up enough, it ends up being more the consistency of like concrete, especially if it gets packed down. But it will end up being flakes and kind of more like potato chips as it flakes off the shell of the vessel. Scale is bad for your boiler. It affects the efficiency of your boiler and your heat transfer. And the effects of scale are typically hidden until you open up the water side for your annual analysis or whatever. And then you see scale. Or you will have the issues with scale because you'll have scale build up on one side of the boiler or the other, and it will insulate part of the boiler from water getting to that part, and that part will overheat and crack, and then you may have a leak. This can also happen with like ends of tubes. If you have scale build up on the backside of your tube sheet, you can overheat the ends of tubes and they can crack, and then you can get a leak. And the leak is essentially just from the lack of cooling from the lack of heat transfer. Scale, once again, a minor amount of scale, just like soot, can add up to a large amount of fuel losses. So even just a 1/64th of scale thickness can equal to about 1% of fuel losses. And if you get bad, like an 1/8 inch of scale, which once again, it isn't much. I've seen boilers easily with an 1/8 inch of scale. It can be 20 to 25% of fuel losses. So that's an increase of fuel. Since scale build up blocks the heat transferring to the water, yet it doesn't block the heat transferring to the metal. Scale buildup in your boiler has more potential to cause the metal to blister or crack, unlike soot, where soot actually blocks the heat transfer from your combustion gases actually getting to the metal of your boiler pressure vessel. So scale can easily lead to more destruction of your tubes and your tube sheets and your high stress areas of your boiler where you have a lot of heat transfer going on. If you get a lot of scale buildup there, that is going to affect your stack temperature. Why this is important is if you are running a boiler, you can't always open it up and look at it on the inside, on the fire side or the water side. So if you are monitoring your stack temperature, you need to know where it should be versus where it is right now. And if you have slow scale buildup on your water side and your stack temperature is slowly increasing over the course of 6 months, if you are monitoring it and tracking it, that means something is changing inside of your boiler. And that something is either going to be soot or scale, and you can end up finding out which one typically from just doing some water testing. That should be easy to find hardness in your water. Hardness causes scale. Or you do a flue gas test and you check with a combustion analyzer and you check what your combustion analysis will be. And if you have a combustion issue, you should find something that is going to cause the formation of soot. And that is assuming that everything is normal, that the burner head is normal, that there's no blockages of the flame or direct flame impingement. If you have something turn on your burner head or nozzles fall out, you can have uneven burning and gas mixing, which can cause soot. Or if your head turns and the flame is pushed right against the wall of your furnace, now you have direct flame impingement and it's going to cause incomplete combustion and cause soot. So assuming that that is not happening and only a combustion analysis is going to show that you just have the improper air and fuel ratio, you should be able to see when your boiler is sooting. You can also see it if it's bad enough that if you have a sight glass into your furnace, you can see soot will typically glow, and you'll see all these like glowing little particles along the surface of the boiler. If you get large chunks, there'll be large black chunks that are glowing, almost like embers or coals. If you were looking at like a campfire, they glow as the fire and heat go across the surface of the soot. Once again, enough soot buildup can become explosive. I have never seen soot be explosive, but I have seen it catch on fire in small quantities. You obviously don't want that because now you have an uncontrolled burn of fuel, and that can become an issue. If you are running a heavier fuel or even just number 2 fuel oil, which is classed as a light fuel, you have opportunities for soot buildup, but you just need to be very mindful of the fuel you are burning. Number 3 is going to be short circuiting. So on a boiler, you'll have baffles or gaskets, and you'll have a ideal path of flue gases for combustion. So you've probably heard of a 3-pass boiler or a 2-pass boiler or 1-pass or even a 4-pass. That's a common Scotch Marine term to classify the boiler by the number of passes. I would probably say that 3-pass boilers are the most common, A one-pass boiler is going to be like a seller's boiler. Their one-pass boiler, I believe, that's the only one I can think of right now, is going to be one pass. You have the fire and combustion process on one side. You have one pass down the tubes, and it goes out the stack. Two-pass boiler, you're going to have fire and combustion process on one side. It's going to go down the tubes, and then it's going to come back through another row of tubes and then go out the stack. Three-pass, down, back, down, and then four-pass, down, back, back. How this affects stack temperature. So if the flue gases are not taking the intended route through the boiler and they are short-circuiting, either through a lack of proper gasketing or a lack of baffles. So baffles are metal plates that kind of direct flue gases. Baffles are typically found in water tube boilers. And if you don't put all the baffles in a boiler when you build it, or if you do maintenance and don't put the baffles correctly, or they move or whatever, you'll short circuit the flue gas. So instead of the flue gases going over all the tubes and through the designed path of the boiler, it will short circuit, and the combustion process or the combustion flow of the flue gas will always take the path of least resistance, and the least resistance is going to be between the source of the flame, so the burner head, versus the stack. So if it can find a shortcut through those two areas, it's not going to just wander through the boiler randomly unless it's forced to by baffles and gaskets and engineered flow paths. So if you remove all the baffles out of a water tube boiler, you will significantly increase the temperature of your flue gas, because now the flue gas is not traveling through the entire boiler. It's just basically coming in, going over a couple tubes, and then going out the stack. If you don't have the proper gasketing in a boiler, sometimes you can have a short circuit between the first and second pass, and you will have a mix of flue gases going between one pass versus they are shortcutting a pass on the boiler, and you will increase the stack temperature of the boiler. All this to say is you need to determine what the stack temperature of your boiler is. What is the proper stack temperature for a boiler? Well, I don't know, because it's a guess, because every boiler burner design combination and conditions all change the stack temperature. There's no, this is a good stack temperature, that's a bad stack temperature. I will say, if you have a boiler and your stack temperature is 500, that is different than if you have a boiler and your stack temperature is 1000. I don't think any boiler is going to have a stack temperature of 1000 degrees. If that is your stack temperature, that is not normal. But there is no such thing as normal stack temperature for all boilers. There's no one size fits all, but there's a range. And how to find that is, one, manufacturer's documentations on that range. This is what it's going to be. Another thing that affects stack temperature is your water temperature or your steam pressure. So a higher steam pressure is going to raise your stack temperature, because the stack temperature cannot be lower than your equivalent steam temperature for that pressure. So if you have a 2 psi steam pressure, your stack temperature is going to be much lower than if you have 100 psi steam pressure, with everything else being equivalent, because 100 psi steam is hotter than 2 psi steam. Same thing with hot water boilers. If you have a condensing hot water boiler and you are running 100-degree water, your stack temperature is going to be lower than the boiler running 180 degrees, just because the medium of the boiler, which is the water, the temperatures are different, and that is all things being equal. So how do you determine proper stack temperature? from the manufacturer, or you record it at startup and you document it, or you record it after a deep cleaning of the boiler. So you punch all the tubes, you clean all the tubes out, you make sure there's no soot or solids build up on the fire side of the boiler, and you clean the water side, and the water side is clean, everything looks good. Record the stack temperature. It should be within 5 to 10 degrees of that temperature. Now that temperature, it's going to change as the air temperature changes, but it should be within 5 to 10 degrees of that temperature with all things being equal. If you notice it going up, something else is changing inside your boiler, and you need to look into it. Typically, it's going to be you're following up on your water side, and you need to do more water treatment and make sure that you are not having hardness build up inside your boiler, which is called scale. You also need to remember that stack temperature will change based on the firing rate of the boiler. So the stack temperature at low fire is going to be different than the stack temperature at high fire. The high fire stack temperature is going to be higher. So with all things being equal between low fire and high fire, the mass flow rate of the combustion gases increases at high fire, and since the heat exchange surface is the same from high fire to low fire, the stack temperature will increase. So whenever you're taking your stack measurements and your readings, the firing rate of the boiler needs to be relatively the same. Another thing that affects stack temperature and can raise it is excess air. Excess air is the amount of air above stoichiometric combustion, and that's basically the perfect air and fuel ratio. We need excess air in order to ensure safe combustion. The ideal amount is 15%, which equals to be about 3% O2 across your entire combustion range. If you increase the amount of excess air, so if you have 1 part of fuel versus let's say the normal part is 3 parts of air. If you go 1 part of fuel for 10 parts of air, you are now going to have a higher excess air. So you have way more air added to the combustion process than you really need. That causes waste. So that essentially does 2 things. It cools down the flame temperature, which reduces the radiant heat transfer of the flame. But then that also is a byproduct of that is the adding of the excess air increases the total volume of the combustion gases, with all things being equal, because the heat transfer area is remaining the same throughout this entire process. So now that we have an increase of air, so we have more mass flow of air going through the heat exchanger of the boiler, that increases the velocity across the surfaces, so you have less time for the flue gas to exchange heat with the metal, with the water, and therefore it will increase the stack temperature. Why this is important? For 2 reasons. Increase the stack temperature does 2 things. It can cause more damage to your boiler. So once again, scale can insulate the water from pulling away the heat from the combustion process, which will increase the amount of heat on the metal. You can overheat the metal of the tubes of your tube sheet, and that can cause blistering and cracking of your metal, which is never good. The second impact of high stack temperatures is going to be energy cost. Typically, production facilities, the cost to make steam is one of their highest cost because it is so energy intensive. However, there's so many leaks from a steam system of where efficiency can leak out of the system if you were looking at a whole system in its entirety, and all those leaks end up being the more production of steam. So if you were to have steam traps that are not working you would end up having to increase the amount of steam production, because now steam is just blown by all your loads. You don't have steam traps. But there's all kinds of things like missing insulation on pipes, which causes more load, which ends up increasing steam production. So a given fuel cost of, say, $100,000 a month, that may be viewed as a normal thing. That's the cost of just doing business. But however, 20 years ago, the same exact design and the same exact equipment, the fuel cost, all things being equal, could have been 30% less than what it is now. And fuel costs has increased by 30% without people knowing, because they don't actually know the data and they don't actually know why they are paying the bill they are paying. And that's why it is so important to have maybe an energy audit or a contractor come in who actually knows what they're doing. It's a big if. And to look at your whole system as a whole and to see if there's any small points where you can increase efficiency of the entire system and get some big wins for efficiency. A big increase of efficiency is an economizer. So stack temperature is what it is. You can only get it so low, but if you can keep recovering heat out of the flue gas before we release it up into the atmosphere, that is always a little increase of the efficiency of the entire system, and that is what an economizer is. So an economizer typically will preheat the feed water. So it will pull heat away from the flue gas after it has left the boiler and will put some of that heat into the feed water that is going to be entering the boiler. So the less you have to heat your feed water, the more you're going to increase the overall efficiency of your entire system. If you are pumping in feed water at 40 degrees into your steam boiler, the boiler has to heat that feed water from 40 degrees to whatever temperature that you have it at steam pressure. If you have 2 psi steam, that's going to be around 214 degrees or whatever it is. You have to heat that 40 degree feed water all the way up to 214 degrees. And that all takes energy. So if instead of the energy going into the atmosphere, if we can put some of that energy into the feed water and now pump it into the boiler at, say, 120 degrees, that delta between 120 to 40 degrees is the difference in energy savings. You can also, and this is typically only done on large water tube boilers, but you can also have an air preheater and preheat the combustion air. The hotter the combustion air, the more efficient your process will be, or the combustion process, because all of the combustion air that enters the burner has to be heated in the combustion process. And I am not a thermal energy expert. I've never taken thermodynamics, but essentially combustion is a chemical process. But if you are using 50-degree air just from taking it from the outside and pumping it into your burner, that air has to then heat up in that combustion process and consume some energy. However, if you take the same air and instead of pushing energy out of your stack into the atmosphere, you take some of that energy and you pump it back into the air that is going into the burner in the air intake. Now that air is 150 degrees. There's a delta between 150 degrees and 50 degrees of savings of how much you have to heat the air for the combustion process. And that savings is a decrease in the amount of fuel required for the amount of steam generation in that example. However, air preheaters, not super common on smaller-ish boilers. They really are only large industrial water tube boilers that I've seen them. I've only ever seen them a couple times. not super common. The more common is an economizer. Now, you may be asking yourself, well, why don't we just cool the stack temperature till it's basically ambient? That is an excellent question. So basically, two things from my understanding. Once again, this can be a deeply complicated topic, and the physics and chemistry of combustion and efficiency losses. There are people who spend their entire careers around this, and I am more of a surface level learner than a deep physicist. But essentially, with a economizer, if we were to pull out all the temperature and excess energy, two things would happen. Number one is, if we were to pull out enough temperature out and energy out of the gases that we would cause the gases to condense, the gases would be either condensing on the boiler surfaces or on the surface of the economizer. And when you condense gases, the condensate is acidic, and that acidic condensate will corrode the surfaces of the boiler and the economizer. You can have a condensing economizer. It will just cost more because it is stainless steel. That is essentially the magic behind condensing hot water boilers, is the condensing of the flue gases, which is pulling and recovering that latent heat before it exits out of the boiler flue gas and into the atmosphere. That is why condensate neutralizers are required on condensing hot water boilers, because the condensate that is generated is acidic, and that is why condensing hot water boilers need to be stainless steel, because if you were to use a carbon steel boiler or a copper fin boiler, the boiler would be super efficient until the heat exchanger corroded away and leaked because of the condensate and its acidity. And then number two is mass flow rate and back pressure. But basically, at a certain point in time, you have to give flue gases an exit on the boiler. You can't just pump against a wall or like blockage. So if we were to decrease the mass flow rate of the flue gases basically down to zero, we wouldn't have any flow through the boiler. So at a certain point in time, you have to keep flow, with everything being equal, keep the mass flow rate of the flue gases to the boiler. And while doing that, you will lose energy, just because there is no way to capture all the energy out of the flue gases and as they are flowing. You can add turbulence to the flow gases with baffles or turbulators, which are metal things that go into tubes that cause the flue gases to not take straight paths. And there's all kinds of things that manufacturers will do. But at the end of the day, you can't stop the flue gas and have it just sit in a spot in order to extract all the energy out of it. And that's all I'm going to say on that. I'm not going to pretend I know the science behind the mass flow rate of flue gases and why an increase of back pressure can't essentially be infinite. That is going to be more of a guest. I'll need to find a guest for that. So if you know somebody that can talk in depth about that, I would love to have them on the podcast. But essentially, you just can't trap flue gases forever. But the biggest savings will be a economizer, and if you can swing, if it makes sense, a condensing economizer, that can also be a huge savings. You want to look at the savings of your entire steam system or your hot water system. An entire system will have more opportunity for savings than it will just looking at the boiler, because the boiler is only one part of the system. All of the energy is made in the boiler, but if you are constantly losing unnecessary energy outside of the boiler in the steam system or out of the stack, then you will never be able to make up all the savings in the boiler. But just to recap, stack temperature tells you three primary things. On the increase, it's going to be soot buildup on the fire side of the boiler, which insulates the combustion gases from reaching the heat transfer surface of the metal. You can have scale buildup on the water side of the boiler, which stops the water from receiving the heat transfer from the flue gases, but the flue gases are still heating the metal, which can cause cracking and blistering of the metal, which can get very expensive. And also, the third is excess air. If you have excess air in your combustion process, it can cause an increase of flue gases due to an increase of mass flow rate through the heat exchanger of the boiler. So hopefully that made sense. If I said anything wrong, please let me know. I'm always open to criticism. I'm always open to other experts coming on the podcast and explaining things better than I am. I am not the expert on everything. And deep physics of combustion and thermodynamics and boiler efficiency, it can get pretty in-depth with how you go, and a lot of manufacturers have spent a lot of time trying to optimize every single point of a boiler and a steam system in order to increase the total efficiency. But the problem is with people going between jobs and a lack of clarity of the data, over time, an entire plant can have an increase of fuel cost and operational cost, but nobody understands the why behind why they're spending that much money on fuel and operational costs of the plant. And there's no good historical data. And that's why it is so important on a startup to document everything correctly. And that is your baseline. That is your zero. So assuming everything is correct with that boiler, all that data should stay the same over the lifetime of the boiler. If your stack temperature is 550 degrees at startup on low fire and at high fire at 650 degrees, those are just two made up numbers. Over the life of the boiler, your stack temperature should be right around 550 degrees with everything else being equal, the ambient temperature being equal, everything should be the same. 550 degrees on low fire, 650 degrees on high fire. If it rises from there, you have bypass going on, you have soot in your boiler, or you have excess air that is not needed in your combustion process, you have scale, buildup. All those things can add up to losses of efficiency. And that is why it's so important to document everything on startup, document the zero so that you know what is good, what is bad. And that's also a good implementation of AI. If you have AI, and this isn't done at scale yet, but it will be done at scale. If you have AI looking at all your data and your numbers and you're recording your numbers somehow, whether it's a building management system, and if a plant is looking at all those numbers and AI is analyzing it, and it can spit out a report and says, hey, over the past 2 months, I've noticed an increase of stack temperature on your boiler. I've also noticed that the fuel flow is increasing, and whatever, this is different than the historical data in the last 5 years. I recommend checking these couple things. And now your system is telling your operators, hey, something is wrong, versus having to train your operators on all the tribal knowledge and the plant knowledge and on all the data of, hey, this is what normal is. Because let's be honest, a lot of times operators are just there to do their job. A lot of times their job isn't to look at the bigger picture. And just with people rotating through jobs and just the loss of knowledge and the learning process, a lot of plants are running with inefficiencies that don't have to be there. And the cost of doing business isn't actually the real cost of doing business. So that is a good way that AI could probably be implemented. How to implement that, I have no idea. It's going to take some time and some trust and some good integrators to implement that, to look at it, but I am sure it's going to happen. But just keep in mind stack temperature. It is a symptom of how the boiler is doing, and you want to keep it in your toolkit of looking at the stack temperature and seeing what it is versus what it could be and making any suggestions or changes from there. And that's all I have for you today. Hopefully you learned something. If I said anything wrong or if you have any comments, you can DM me on LinkedIn or email me eric.johnson@boylearn.com. If you want to be a guest or have a recommendation for a guest, you can email me or DM me on LinkedIn as well. I would love any feedback. If you haven't already, please rate the Boiler Wild podcast 5 stars. I appreciate you for listening, and stay wild.